Good afternoon. We continue our discussions on there are four new devices which we are talking about. The first device which we've done two already in the class, and some of you who were in the tutorial yesterday and on Monday you did some tutorials, and I think there's two tutorials tomorrow. So you would be doing problems on these particular devices. So the first device was a multiplexer. A multiplexer is when there are multiple data lines. There's a lot of data coming in from different channels, right? And all you want to do is you want to look at one channel at a time. So for example, if you've got a television, right? If you've got a television, and let's say you've got, right now in Fiji, you've got, how many channels do we have free to air? You've got, right, okay, let's say 8. On YLSE you've got 8 channels, right? So on the air, there's 8 electromagnetic signals coming in. 8 different signals coming in, right? Okay? And you've got only one TV, so you can only view one channel at a time. So what do? You tell your set-top box, which is a multiplexer by the way, right? The decoder is a multiplexer. That YLSE box is pretty much a big version of the principal component is a multiplexer. So all you're doing, okay, I want to watch channel 1. So what it does is it flips over to channel 1. You want to watch channel 2, channel 3, channel 4, channel 5. So what a multiplexer does is, there's two components. One is the data. There's 5 or 10 different channels, so many different channels of information coming in, different channels, different signals from a sensor, different radio, different video signals, right? Okay, whatever it may be. There's the selector, which is in this case your remote control, your selector, so your selector lines, and then only one output. Remember, that's the key part. Only one output. Only one output. All right? Okay? So you use your selector lines to choose which line will be, which channel is the chosen one to come and be displayed. Which channel would be the chosen one to be displayed on your which channel would be the chosen one to be displayed on your output channel, on your output, right, on your TV. All right, now there's another device. So that was the multiplexer. But to build a multiplexer, it can be quite tricky. Okay, it can be quite tricky. So let's have a look at what the situation is. So let us say we're looking at the week 8 notes. All right. Okay. So let me just do a quick review over here. So if you look at output lines in your truth table, if somebody, remember, always we give you a black box, right? We give you a black box concept, a block diagram. Like for example, when you did your midterm exam, you had a block diagram of 4 judges, not a block diagram, but it was like there's a word problem, and then from what that you understood was there were 4 judges, so there's four inputs, but only one output, the yes or no light. Not 4 judges, I think it was 4 security sensors and only 1 security lamp, yeah, in your midterm exam, right? 4 security sensors and one particular security lamp. All right. So what was the case? Oh, by the way, guys, I'll just make an announcement. Your midterm result is already ready for pickup. You go either to pick it up from the Wednesday evening lab session. You can pick it up from the tutor there, right? The Wednesday evening lab session, or the other one is you can pick it up from the Friday lab session. So one or the other. I'll let you guys. So just spread this news around. So it's either the Wednesday evening tonight. You can go and pick it up tonight, your script, and you can pick it up on the Friday lab session. One of those 2 lab sessions. All right. Okay. Now let's come back to here. So there was in our black box over here, our block diagram. There's only one output. It's quite obvious. But there are 6 inputs. But because there are 6 inputs, that means if you draw a truth table, 6 inputs, 1 output, that would result in that would result in 64 combinations to the power of 6. 64 combinations. That's a bit too difficult. All right? Okay? So what do? The next option is to redraw our truth table like this. So let me just draw it. This is just a revision of our. So you have, this is your output F. So drawing 64 line truth table is too hard. So we have this, we have S0, S1. The least significant selector, most significant selector, 2 selectors, right? Okay, so input side 0, 0, 0, 1, 1, 0, 1, 1. All right. Now, 0, 0, which output becomes D0. 0, 1, output D1 is connected to F. 1, 0, data line D2 is connected to output F. And this one, D3. So this is another way, just in the case of our multiplexers, this is one way of representing our truth table. You won't be able to do it for other systems, like for example your midterm exam, you won't be able to do it. Why? Because over here in multiplexers, at any point in time, only one of the input data lines gets connected to our output F, right? It's like a connection, just like our TV channel where you pressing the button and you just connected only one channel, right? So luckily our truth table can be reduced to this rather than having a 64 line truth table. Now once you do this, then we can say that, hey, for this line here, F will equal to D naught S1 bar S0 bar. D1 S0 bar, S1 bar S0. D2 S1 S0 bar. D3 S1 S0. There we go. All right? Okay? So what do we have? Our final F will equal to all of those ones. D0, S1 bar, S0 bar, or D1, S1 bar, S0, or D2, S1, S0, or D3, S1. So in the end, that's our function F. Now if somebody were to ask you to build a multiplexer for 16 input data inputs, straight away you'll know, hey, how many outputs, guys, in this multiplexer? 16 inputs, therefore how many outputs? Will always be 1. There's no calculation. How many selectors? Will be 4 selectors, right? But then, hey, if we were to do this the traditional way, if you can do this the traditional way as well. The traditional way is what we learned early on, right? But what would be the result? It would be 64 lines on your truth table. That becomes too hard. Now if it was a 16 data lines coming in, how many selectors have we calculated? 4 selectors. Output will always remain 1. So therefore how many inputs? It will be 16 plus 4, which gives you 20 inputs. So therefore in your traditional truth table, how many combinations would you have? You'd have 2 to the power of 20 lines in your truth table. What is 2 to the power of 20? 2048. 2048 lines on your truth table. That becomes too difficult, right, to handle. Right? So that's why you'll do it something like this. Okay? Alright, now the next device we learnt about was a decoder. And I'm doing this in a particular pattern. So from mux we move to decoder. Decoder. Decoder is slightly different. Decoder, in our multiplexer, only one output. Decoder, you've got two inputs, right? Okay, so you can think of this, the input side is binary. The input side is the binary combination. And the output side is only the what do you call, the decimal conversion. Right? Think of it along those lines. Right, so how do we handle that? Well, the input side is binary, and your output side is decimal. So if you have, let's say, 0, 0, 0, 0, output 0 will become high. All the others will become low, right? What example did I use in Monday's lecture? I said, sorry? Oh, traffic lights, yeah. So at any one point in time, only one light can turn on, right? So, yeah, so you put a binary combination here, the code, binary code for which light you want on. So let's say you want light number 3 on. So you'll have 1, 1 going in there. If you have 1, 0, light number 2 will go on. And all the others will turn off, right? So at any point in time, only one output comes in. So guys, tell me, this is a block diagram. What's sitting inside there? There's actually 4 outputs. So let's talk about our truth table. The moment you see the block diagram, you start to think about your truth table. Once you get your truth table, you can get your equations, either by doing some Boolean algebra, sum of products, product of sums, sum of minterms, product of maxterms, Carnot maps, so many methods you've learned. All right, now, over here. For this, the truth table will have, what will our truth table look like for this guy here? Our truth table, input side, how many inputs? 2 inputs only. But how many outputs? 4 outputs. So for every output, you need a Carnot map. Every output, one Carnot map. Okay? All right? Every output, one Carnot map. Or you may not, Carnot map may not be necessary. You can simply do a sum of products method over here. Let's draw the truth table for this. Have a look at that. So you have your input. Your least significant is A0. Your most significant is A1. Your outputs is A03, O2, O1, O0. All right. Now let's come here. 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1. This is standard input combination, right? Now, at any point in time, okay, if 0, 0, which one lights up? Okay, let me just renumber this correctly. That's 0, 0, 1, 1, 0, 1, 2, 3. Okay, but still, even if you mix it up the other way around, doesn't matter. The output doesn't change because you only look at one output line at a time. So, if 0, 0, which one will turn on? 0 will turn on. All the others will be off. This will turn on. All the others will be off. This will turn on. All the others will be off. This will turn on. All the others will be off. So instantaneously, you don't need to do Carnot map in this case, right? Because only at one point in time, only one is on. So you can just use the sum of products. You can say, hey, O is equal to, what can you say over this? O is equal to, so you only look at the O line, yeah? Don't only look at the one line. Don't start looking at the others. One output is one circuit, yeah? One formula, one output, right? In our earlier case, that was F was one output, so you have to consider all this. That's why it's a long equation. Over here, straight away, our equation O is equal to A1 bar A0 bar. O1 is equal to, let's look at O1, is equals to A1 bar A0. O2 is equals to A1 A0 bar. O3 is equals to A1 A0. There we go. There we go. So therefore we got 4 equations. Why 4 equations? Remember our block diagram had 4 outputs. So therefore 4 equations means you'll have 4 sets of circuits, but all sharing the same set of inputs. Right? All sharing the same set of inputs. So this will look like, I'll just do a rough, not the correct one, but this will look like something like this. Okay, I'm just going to do partial of it. Okay, so that's A1. This is A0. Obviously, what comes here, guys? This will be A1 bar. This will be A0 bar. And let's do the first one. So there will be A1 bar. Can you guys see this? Yeah. Okay, there. And A0 bar. And you have your NOT gate. And this is O0. And what's the next one, guys? Next one is O1. That's A1 bar. Right, and you have A0. Oh, and this becomes O1, O0, O1. right? So you guys get the picture, and then I just drawn partial of it. There's 2 more. So do you see what's happening over here? 2 inputs, 4 outputs. Yeah, that's the professional way to do it. And that's only half the circuit. There's 2 more AND gates still missing. Guys, quick question now before we move to demultiplexers and decoders. We have only done encoder and multiplexer. So this here was a encoder. All right, guys. Now, if you have 8 outputs to control, let's say your traffic light is for not just maybe a T junction, and you've got 8 lights to control. So at any point in time, only 1 light to turn on. Let's just assume, right? Or you've got some kind of a system where at any one point in time you've got some disco lights and you want only 1 light to turn on, right? So have you guys seen the stream of so let's say you've got some kind of streaming lights. You know what a streaming lights is? Usually for Diwali they put on lights. So if you've got a string of lights and you want to light this, then that, then that, then that, then that, right? In a sequence, you want to make a sequence of lights, right? And then turn this one on again. You guys getting what I'm saying over here? So you want to make some decorative lights over here. You want to make some decorative lights, right? And at any one point in time, you only want to turn on 1 light. Then you want to move to the next light and everything else. Then 3rd light, then 4th light. So you see, the lights only come on 1 at a time, right? And you want to have, let's say, 16 lights, 16 LEDs, right? So what sort of decoder will you have? 16 LEDs. What encoder will you be using? At one point in time, only 1 light turns on, right? So you'll have a 4 to 16 encoder, 4 to 16. How do we know 4? Well, 16 is 2 to the power of, 6. Okay, what if you had 100 lights? 100. Imaginary decoder. Let's say you've got 100 lights to do, and you want to just make a line of lights, and only the light travels. The LED, which LED turns on and off, right? Travels. 100, 100. What decoder would be good enough for that? 4 to 16? Nah, 4 to 16 won't be able to do it, because 4 to 16 can only handle 16. So what would be the number of inputs into your encoder? Sorry, I keep on saying decoder, it should be encoder. 7? Yeah, so you're trying to build, let's say if you were asked to build this, it'll be 7 inputs, and output there'll be 100. Not 100, it's actually 2 to the power of 7 is 128. So the last 28, you don't connect it to any LED at all, right? The last 28, you just leave it blank, don't leave it dangling, right? Just terminate it over there, all right? And only the first 100 you're going to connect, right? You get it? Okay, and the other point I made in Monday's lecture was, hey, if you've got a small multiplexer, let's say if you get that 100 problem, right, and you've got to do decorations or whatever, the way to do it is use smaller decoders. Let's say you only had the 3 to 8 decoder, right? The way to do it would be to build bigger decoders using smaller decoders, right? And let me give you a hint over here. To build smaller, remember I wrote this problem on your board, right? From big to small is easy. What do? We gave this problem already on Monday. Going from big, let's say if you've got a 3 to 8 decoder, or if you've got a 8 to 1 multiplexer, and you want to just build a 2 to 1 multiplexer or a 4 to 1 multiplexer, all you got to do is just tie one control line, one selector line to ground, the most significant one, right? And same thing goes for a decoder, right? Same thing goes for a decoder. If you've got a 3 to 8 decoder, let me just flip back to the computer. If you've got a 3 to 8 decoder, where is this? That's there. If you've got a 3 to 8 decoder and you want to, that's the only thing available. And they say, no, but we just want to use 2 lines from there. So what are you going to do? You take the most significant line and you tie it to 0. You tie it to ground, right? You connect it to a 0. 0 is a ground. And you only use the least significant bits, and therefore you'll only be using, that will transform itself to a 2 to 4 decoder. 2 to 4 decoder in this case, all right? Okay, now, okay. What about the other way around, guys? What about the other way around? How about if you wanted to build something big using something small? Remember, I asked you this question. You can go downwards, you can upgrade as well. Obviously, if you wanted to build, let's say, you wanted to build one 3 to 8 decoder using using a couple of X number of 2 to 4 decoders. How do you do that? Well, simple. Let me just show you the circuit. Build 3 to 8 something like this, guys. In fact, that's the answer probably. There's always on the decoder line, one switch which is called the enable line. All the switches, all your particular chips. I don't know, when you guys use the NAND gate, I know you've been using NAND gate and N gate in your labs. Was there an enable line over there? Okay, for N gate and NAND gate, there's no enable line. But as you move to encoders, decoders, these higher level chips, yes, there is an enable line. And all the enable line does is turn it on or turn it off. Right? It's like a switch. Turn the whole chip on or turn the whole chip. Power up the chip or power off. Even though you're already supplying, there's a VCC somewhere over there, you're already supplying energy, but it enables it, meaning it allows it to, okay, yeah, okay, take in the data or start working, you know, like a switch on and switch off. Just like your TV, you've connected it to the power point, you've turned the power point on, but the TV won't turn on until you press the on button. Yeah? Alright? Okay, same thing goes over here. That's just like the on button. Okay? Now, what it's doing is, you see, you wanted 8 lines out. You wanted 8 lines out. But you only have a few, right? All you've got in stock is one box of 2 to 4 decoders. How do you build a 3 to 8 decoders? You can use as many decoders as you want. So what do? Right? Well, these 2 is here, right? That's your 8 lines out. And all this guy does is it controls your enable line. That controls your enable line. So, yeah. So if you want to turn on this one, because remember, at one point in time, only one line will come up. Only one line will come up. So if you have your input combination such that, let's say your input combination is 0, 0, 0, 0, oh sorry, 0, 0, 0. So you only want to turn on this one. So you've got to do it in such a way that your input line over here, that'll be tied to 0. That'll your x2. This is x0. That's your x1. Okay. All right. Let me show you this on the paper. So your 3 to 8 decoder, A0, A1, A2, and which output turns on? Which output? Right? Which output turns on? So if 0, 0, 0, it'll be D. I'm just trying to be consistent. They use the letter D. Yeah. What letter are we using in our notes? Just to be O. Okay. So O and D. All right. So this 0, 0, 0. So output 0. Output 1. Output 2. Output 3. Output 4. Output 5. Output 6. Output 7. Guys, I could have drawn this truth table. You could have come up with a very long truth table, and you can imagine it. It would have been all 0, 0, 0, 0, 0, and only 1, 1, 1, 1, 1, 1, 1, 1 going in a diagonal. So I've just done a shortcut truth table over here, just because we know everything else is 0, right? Okay, so those are the combinations. Now, take a note over here. If you want to select, right? If you want to select anything from 0, output 0 to output 3, output 0, output 1, output 2, output 3, right? What can you comment about the most significant bit of the input? It will always be a 0. Can you see that? If you want to select anything from output 4 to output 7, what can you say about the most significant bit of output 2? Of the inputs. It'll be always a 1. So that's where you're going to play it. Right? That's where you're going to play it. So basically, if this is a 0, right? Let's look at our solution over here, the solution which was online. So take note of this. This is the key part. That if you want to select 0, 1, 0, 1, 2, 3, this guy here will always be a 0. If you want to select 4, 5, 6, 7, this guy here will be a 1. And these two combination, can you see these two? 0, 0, 0, 0, right? So 0, 0 will be, will be going on to your second line. Okay, so now have a look at this. There we go. Have a look at this diagram. I'm not sure if it's too clear. Let me just zoom in. There we go. All right. Can you see your most significant? Remember, we were only given, you went to your technician and the technician said, sorry friend, we've only got 2 to 4 decoders. But what do you want to build? You want to build a 3 to 8. Oh, you'll need, take a couple of 2 to 4 decoders and put it together so that you can build a 3 to 8. So how do you do it? Right? Now this is what your real design. Remember, our course is digital logic design. You've got to think as a designer. What can you do with your current pieces of the puzzle to build the final outcome? Right? So that's what we're doing. All we're doing here is playing with the enable line. So can you see the most significant bit is already tied to a 0 over here? You see that 0 over there? Right? And that's your x2. Right? So when this x2 is a 1, this one is already a 0 because you don't have a fourth input, right? When this is a 1, right? So what line gets collected? 0, 1 means D1 will get selected. D1 is connected to enable here. This guy comes alive. Right? What about the other two inputs? It's x0, input 0 and input 1. Input 2 is the most significant. Right? In our truth table I use the letter A, I think. Over here they're using the letter X. So just take note of this. Right? And just do a search. What did I do? I said 3 to 8 decoder using 2 to 4 decoders. Right? Okay, so that's x0, x1, it's a0, a1. And that same a0, a1 gets fed to this guy and this guy. But we want to make a difference. Which one to select? Yeah? Take this home, have a think about it. All right? This is a real design problem. Right? And this is what you'll be facing. You'll do this lab. The reason why I'm taking time to discuss this problem is because you'll be doing it in your lab starting Monday. Monday's class was there, but you'll be doing it more of it as we go on. All right? Okay, so that's a real design problem. Hey, when I switch over to this, does this get recorded? Does the website get recorded on the? Does this image get recorded on the video? Okay, all right. So at least you guys can have a look at the solution. All right, okay. Now I want to talk to you about now the other way around now. So far we've been talking about multiplexers, right? And then how we've been multiplexers and decoders. And what did I say? Hey, how do we build a smaller decoder from a bigger decoder? And how do we build a bigger decoder from a smaller decoder? Same thing goes for multiplexer. How do we build a smaller multiplexer from a bigger multiplexer? And how do we build a bigger multiplexer from smaller multiplexers? Same story, all right? And that's a real design problem, and definitely you'll get that in your final exam, all right? Or maybe short test number 2. All right, now another application of multiplexers was this, guys, right? And I showed this on Monday. So right now, until now, we've been doing a repeat of Monday's lecture, right? That you can have a sum of minterms, and your multiplexer can be represented using your sum of minterms. Your multiplexer can be used to represent a sum of minterms. Right? If you were to do the Carnot map process and all that, okay, what we'll do is there's some time constraint in doing the design because you've got to do it into the Carnot map, and then from the Carnot map you've got to do this minimize sum of products, and then from there you will have n gates and you'll have one OR gate, right? So because n gates sit on one chip, OR gate sits on another chip, that's 2 chips. Even though you've already minimized it, it's 2 chips. And if each chip costs 20 cents, that's your total cost is 40 cents. This one multiplexer chip will still be maybe 22 cents or 25 cents, right? Expensive than a one N gate chip, but less than buying 2 chips, one N, one O. See what I'm saying? That's why we got to do this, right? That's why this becomes a cheaper solution. All right, now let's now look at the other thing called a demux. We've spoken about multiplexer. Now we speak about demultiplexer. Okay, I start off from slightly complex, then I go easy. Let's have a look at demux. A demux is opposite, in plain English, a demux is an opposite of mux. All right, okay? So it's like one data line, and you are telling it to go to which data line, right? Which area to connect to. So basically, think of it like this. Remember in the old days, nowadays this would be in your in video technology to video and audio technology. Most of these multiplexers and demultiplexers, it's in audio, video, in communication systems. This is where we are using it. In fact, even if you look up security camera, they now advertise this in the newspapers. Security systems, security camera systems. You'll only see the video multiplexer, video demultiplexer terminology. Oh, how much you want a 16 multiplexer or you want a 32 multiplexer? How many cameras do you have? Okay, now in the olden days, just the example which comes through it is was that when you make a phone call and then the lady says, hello operator, and then you say, yes, I'd like to speak to the head of school. So yes, okay, I'm connecting you through. So have you seen this thing here? You've probably seen it in the movies, but they don't do it nowadays. Nowadays you just do a direct call and say, hello professor, and so you call the operator, your data line comes here, and then your operator says, you say, oh, I want to speak to the head of electrical, right? So the operator says, oh, head of electrical is D1. So what they do is D1 is 01, and this line here gets connected to D1, right? So the word over here is anyone worked or done any background or had a hobby in telecommunications? Have you heard of something called PABX? PABX systems. PABX is a telecoms system where one phone line comes in. Right? I think it's probably more than one. I'm not sure about the actual technology nowadays. They make it more, but the concept is the same. One line comes in. It's one line, right? Okay. Yeah, one line comes in, and then based on the coding, it goes to the operator as well, and the operator can patch you through. They call it patching you through. Right, and yeah, and then based on this, they patch you through. Right? They patch you through. In the old days, they actually used to take out the wire, and they used to, oh, okay, head of school is line D0, and then they used to put the wire, plug it in that way. Right? I'll show you the picture. Show you the picture. There we go. Yeah, physically, no joke. This is what they used to do. All right, so you call, and then they say, that's a hello operator, and then you tell them, oh yeah, I'd like to speak to the president, and then they'll say, they'll connect you, they'll patch you in. That's where the word patch comes in, because they take that wire. See, this lady here is just connecting something in over here. There's a wire, and they'll plug you in. Right? Yeah, that's basically a human demultiplexer. But this is a real thing. PABX uses this, right? So for those of you interested in communications, that's what happens, right? Right? Okay, so that's a selector. So it's probably more like you have 4 girlfriends, and then you want to choose which girlfriend to go to date this night. So you throw a roll of the dice, and it says 001. So you say, okay, I'll go to girlfriend number 1 tonight, right? So it's something like that. All right. So same thing, but it's opposite of demux. All right. Opposite of mux. Okay, decoder. The important part is you've understood it already, but hey, I can give you a question and say, build this box, build this demux, but using basic AND and OR gates. How are you going to do that? How are you going to do that? How many inputs, guys? How many inputs in the system? No, 3 inputs. 3 inputs. Selector lines are inputs. Right, just like in your mux, selector lines were input. 3 inputs, how many outputs? 4 outputs. So therefore, you can do your truth table. 3 inputs, 4 outputs. At what point in time will which one turn on? Yeah? Okay? Or you can make a reduced truth table, because at only one point in time, yeah, your only one output will be showing something. Only one output line will be showing something. So D0 will only show when D will always be there. There'll always be data sitting at D. It's only waiting for them to get routed, right? Routed. In fact, there's also some things like nowadays, apart from PABX, you've got routers, you know, internet routers and switches. They use all the same technology, right? Same fundamental principles, right? So data will always be there, and this is basically telling it which line to go into, right? So you can draw your truth table, or you can do a reduced truth table, just like how we did for the mux, right? And please make a exercise down in your, please make a note down in your exercise book. Try and draw the full truth table, and number 2, try and draw the reduced truth table, and from that, try and extract these equations. The equations are already given. All right, equations I've already done for you. So we've skipped a step in the middle of drawing the truth table. All right, so that's a demux. That's a demux. All right, and then after that, obviously, you can draw the circuit. How many inputs, guys, in your circuit? There'll be 3 inputs, but how many outputs? There'll be 4 outputs. Right? Now that we've done the hard one, let's look at the easy one. Can you see what's happening here? Right? 2 inputs, 2 outputs. 2 inputs, 2 outputs. What are the inputs? D and S. S0. Okay? And 2 outputs, D0, D1. So when D0 will, where D0 will equal to D if D1 is 0 and S is equal to 0. And so basically, that's your equation. You can do this in your truth table. Any questions? You guys all right? Okay. All right. So that's your circuit, guys. That's your circuit. Simple circuit. All right, very simple circuit. So again, that's how your demux works. That's your block diagram of demux. We always after every system, no matter how complex, even those PABX systems, you can reduce it down to AND and OR and NOT gates. AND, OR and NOT. 3 gates can build everything. And of course, those 3 gates you can build using what? NAND gates. So pretty much entire systems you can build just using NAND, or you can build using just NOR. All right. Any questions, guys, for this one? All right. Now let's look at another chip. So we've done mux, demux. They're total opposites of each other, right? Same thing, same principle. For mux, 1 output line, right, and many data lines. For demux, 1 input data line, many output channels. Yeah. All right. Encoder and decoder. Firstly, decoder, you've got 2 control lines, and then you select only one output line will go high, which we've just studied. And then there's something else, the opposite. That was decoder. There's something else which is called the encoder. Oh, I think it's not here in the notes. Decoders, encoders. Okay, guys, let me tell you about encoder. Opposite. Just flip this around. Okay, so let's have a look at that one. Encoder is something which will, you select something on this side, one of the possible options on this side, and what it does on the other side gives the binary combination. Just the opposite, right? But generally, decoders are more, because in electrical systems, why would you want to do that, right? It's basically, this is more in use than encoders. Decoders are more in use. Going from binary to select one of the lights, or select one of the speakers, or security systems, or something like that, right? You want to turn on or turn off some particular device, right? One device. Okay. Okay, now let's look at an application. Okay, let me just open your tutorial. So I'm just going to do a preview of your tutorial. For those of you who have not done it, let's have a look at this, guys. Another form of decoder, custom-made decoder, is for this one here. This is a 7-segment display. Why do they call it 7-segment? Right? You've seen this display, right? It's on your calculator and all that. You know, digital watches. You know, many things we like using this. So there's 7 sets of LEDs. 1 LED, 2, 3, 4, 5, 6, 7. Right? So if you want to light up the number 1, what LEDs would turn on, guys? B and C. If you want to turn on the 0, if you want to display 0, A, B, C, D, E, F, right? What about the number 4? A, B, C, G, F, right? F, G. Okay, now if we draw, and let's say if you want a system, you want to build a block, right? A block diagram. On this side, if you're binary, and on that side, you have the right combination which will go into this. So basically, let me just put this on paper now. So they call this the BCD to 7 segment. All right. Okay, in our notes, I just want to be consistent with whatever we've got. W0, yeah, 0, I think. All right. Okay, so we've got this chip, right? This is a BCD to 7 segment converter or decoder. BCD, binary coded decimal, right? Remember, what can we display on that particular 7 segment display? We can only display what? We can only display from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't display the number 10, right? So how will we do this? So if we want binary over here, 0, 0, 0, 0, what should light up? Let's have a look at it. Which one should go high and which one should stay low? So let's have a look at this. So if there was 0, 0, 0, 0 coming in, A will be 1, B will be 1, C will be 1, D will be 1, E will be 1, F will be 1, G will be 0. Right? Forget about this decimal point. That's just another separate line. Okay? But this is what we want to control, these 7 segments. Right? That's why they call it a 7 segment display. Let's take the number 6. Number 6. So 6 will be what? 0, 1, 1, 0 coming into the chip, right? And what's going to be A? A will be 1, F will be 1, G will be 1, C will be 1, D will be 1, E will be 1, B will be 0. So let's try one last number. Let's try number 8, simple number. So on our input side, what will be coming in? 0, 1, 1, 1 onto the left hand side of the chip. Remember, I just drew the chip. And on the right hand side, what will come out of the chip? All of them will be 1. Yeah? A, B, C, D, E, F, G. Right? None of them will be 0. So eventually we will end up with this truth table. Can you see this truth table? That's your truth table. Eventually we will end up with this truth table. So this is your binary combination. All your binary combination. Input side is always easy to populate. You just do the standard combination input. And output side, you have to look. So A, B, C, D, E, F, right? So 0, remember I said we did this, 0, all this will be, G will be 0, right? Okay, now, how many outputs, guys? How many outputs in this chip? That's the chip which we drew. That's there. How many outputs? 7 outputs. Therefore, how many Carnot maps will you be doing? 7 Carnot maps. Hey, but your Carnot maps cannot be completed. Why? Why can your Carnot maps not be completed over here? Well, you've gone from 0 to 1001, which is number 9. So what do we do for 1010, 1011, 1100, 1101, right? And all the way till 1111. Well, you can put zeros over here, okay? Zeros, okay? Because you don't want anything to turn on. Sometimes some people put don't cares. Don't cares is also acceptable. Zeros and don't cares. But don't put a 1 because that means turning the LED on, right? Now, for A then, what do you do? We find the, what do you do for A? We look at we draw a Carnot map. So for A, there's 1 Carnot map. B, there's 1 Carnot map. C, there's 1 Carnot map, right? Okay, for each of them, you'll have 1 Carnot map, right? And therefore, how many Carnot maps altogether in total? For each output, 1 Carnot map. So therefore, 7 Carnot maps, 7 sets of minimized equations, right? 7 sets of minimized equations. And what do we then get? 7 sets of circuits. 7 sets of circuits. All right? Okay? So that's your BCD to 7 segment decoder. So these decoders, guys, are very easy. Hey, if you have a lot of money and you were able to buy, what else could we do? 4 input. Is there any other chip which we could use instead of using N and O? You could use a 4 to 16 decoder to do A. One 4 to 16 decoder to do A, one 4 to 16. So you'll need 7, 4 to 16. That's another alternative. If you don't want to do Kano maps and do the minimization, you can just go via that way, right? Depending on what's cheaper, right? So this would be, you can build using Endo and knots, or you can build using a multiplexer, right? Not 4 to 16, 1 to 16 multiplexer. All right, guys. So in practicality, this is, they call it the 7447. The real deal chip is called the 74LS47. 74LS47. That's the real deal chip. For decoder application, the real application is in memory, to select which memory to access, so which is holding a piece of data. So that pretty much finishes our lecture on decoders. And oh, there's one more point, guys. There's something known as a parallel adder and parallel subtractor. I'll have a look at it in our next lecture. But otherwise, apart from that, we'll have a bit of propagation delay. And next week, so tomorrow we'll have our last lecture on this, on combinational logic. So up till now we were doing combinational logic. From we will start tomorrow on a topic known as sequential logic. Now you'll see that our course in the very beginning was very simple, right? AND and OR gates was very simple, right? And you guys did very well in your, generally you did well in your midterm exam. Now, because the nature of the course, the first half we're doing the basics and the fundamentals, it's easy. Now if you look at what we are doing in week 8, starting to get a bit complex. We are talking about decoders, multiplexers, demultiplexers. We are using our basic knowledge to build complex systems now, right? Now we will move into memory and sequential logic. Remember in the beginning of the very first lecture, we were talking about clocks, counters, stopwatches, sequential logic. That's all sequential logic. In sequential logic, all this combination logic needs to be at your fingertips, right? So we're moving into more complex system. So what I would encourage you is, you guys are already over here and you are attending the lectures. Please send a message out to your friends and to your fellow classmates to attend lectures, because sequential logic gets hard very quickly. Like in week 1, week 2, we were doing binary number conversion. That was very simple, straightforward. You can even, somebody with good mathematical background can quickly pick up on it. And even you guys are doing CS211, there's a lot of overlap between CS211 and first 7 weeks of this thing here. In CS211, how far have you guys gone with digital already? You finished, right? There's a lot of overlap. You guys did some AND/OR circuits and Kano maps. I don't know. Kano maps you didn't? No, but you got some basic stuff there. Now it's going to get complex. It's going to be really complex. And first 7 weeks is like a prerequisite. So in fact, this course has got 2 parts: combination logic, sequential logic. Sequential needs combinational. Combinational should be, I won't teach you now how to do Kano map. I'll just say, okay, you have that there. From the truth table, you get your Kano map. I won't show you, oh, this is group of 2, group of 4, because you already need to know it already.